Hello, everyone. Welcome to the lab on measurements of space and time. So in this lab, we will do a few things. One of those is we will measure the density of a small aluminum cylinder that's in your kits. Like physically, if you do this, your aluminum cylinders in your kits and lab. Um, and while we do that, we will also practice calculating measures of accuracy and precision, which we learned in the other handout and the other videos, right? Calculating how to calculate PRAD, which remember is a measure of precision, and then how to calculate percent experimental error, which is a measure of accuracy. Okay, so in the first part of the lab, we're going to ultimately measure the density of aluminum cylinder. But to do that, we need to measure the mass of the cylinder and the volume, right? If you remember, density is equal to mass divided by volume. So let's start with measuring the volume of a cylinder. So if you think about it, right, a right circular cylinder has both a diameter, right, or a radius. You can think of the diameter as being twice the radius, and a height. So we need to measure those two lengths. We need to measure the diameter of the cylinder and then the height of the cylinder. To do that, we're going to use an instrument called the vernier caliper. And the vernier caliper is a fairly accurate instrument. It has a resolution of zero point zero 0.01 centimeters. So the smallest length that it can measure is zero point zero 0.01 centimeters. So the first thing I'm going to do is show you guys how to read a vernier caliper. You'll have some vernier calipers in lab that you can use. In this video, I'm just going to use a simulation to show you how to read the vernier caliper. Okay, so let me go to that screen. Okay, so here's a vernier caliper. And if you notice, there's basically two scales on a vernier caliper. You have the main scale, which goes along the vernier caliper, and this is in centimeters. And then you have another scale, which is called the vernier scale, which just goes from 0 to 9. And this is on one of the jaws that moves. So this is the vernier scale. This is the main scale. So let's say we want to measure the length of this blue object here. So the first thing you would do is you would place the object between the jaws of the vernier caliper, right, and close this down. So you'll do that when you're measuring the diameter and the length of the cylinder, aluminum cylinder. And then to read the length of this, what you do is you read where the zero is. Sometimes this is also called the index, the zero here. So where is that zero, the zero on the vernier scale? Where is that located on the main scale? And notice here, right? So this is one, right? Or you can think of it as 1.0, 1.1, 1.2, 1.3, 4, 5, 6. So it looks like the zero is past the 1.6, but not quite 1.7. In fact, it's a little bit less than halfway, right? Between 1.6 and 1.7. So we know it's going to be 1.6 something. To get that last digit, the hundredths place, what you do is you look on the vernier scale and you ask yourself which line, which number, 0, 1, 2, 3, and so on, lines up best with any marking from the main scale here. And if you look at this, first of all, just by eyeballing it, because it's less than halfway, it's probably going to be like 1.62, 3, or 4, somewhere in there. So if I look on the vernier scale now, it looks like actually the 3 lines up best. So then I would read this as 1.63 centimeters. That would be the length of this object. Okay, and actually that's what the computer does it over here. That's what it's also getting 1.63. Let's do a few more of these. Let's say this is the length. Okay, let's say this is the length of the new object. So again, I want to read where the zero is on the main scale. In this case, it's past 2.1, right? Because this marking would be 2.1 and not quite 2.2. Eyeballing it, it looks like it's a little bit past halfway, so it might be 2.16, 17, 18, somewhere in there. To get that last digit exactly, I look on the vernier scale. And sometimes this is difficult to do. Sometimes you kind of have to guess. But in this case, it looks like the 7 lines up pretty closely with the main marking on the main scale, right? It looks like it's the best. Nothing else really lines up well. So, and we know it's kind of going to be 6, 7, or 8 anyways, just by eyeballing it. So in this case, sorry, it's a 0 here, right? So 6, 7, or 8. So in this case, the reading would be 2.17 centimeters. 2.17 centimeters. All right. Let's see. Okay, let's say this is another object, right? We want to measure this length. And let's say we get this particular reading right here. So how would we read this? Well, if I look at the main scale, where is that 0? Well, it's at 2.2. And then in this case, the 0 lines up best, right? Because it's right on it. So actually, you would read this as 2.20 centimeters. And you have to give that 0 for the hundredths place, right? So it would be 2.20. Okay, let's do one last one. Let's say this is the length you want to measure. In this case, the 0 is just past the 2. Okay, so the first part would be 2.0. And then to get the last digit, well, it looks like it's maybe halfway, maybe a little bit more than halfway. So I want to focus on like 5, 6, or 7. And I'm going to argue that 6 lines up best. So actually, this reading would be 2.06 centimeters. Okay, that would be that length. So in lab, it's exactly the same thing, except obviously with a real vernier scale, sometimes it's a little bit difficult to read because the numbers are so small, but it's exactly the same idea. Okay, so the first question that you're going to be responsible for from the lab manual is question 4. And if you look at this lab, basically this is lab 1 in the lab manual from Polito, Walsh, and Gagnon, the 10th edition. And basically, it's just going to ask you to explain in words how you use the vernier caliper to measure the diameter and the length of or the diameter and the height of the small aluminum cylinder. So you're just describing in words how you did that measurement. Okay, so you're going to take 5 measurements of the height, 5 measurements of the diameter, right? Again, all these values will be to 2 decimal places, right? Because remember the resolution is 0.01 centimeters for the vernier caliper. And then question 5 is basically to, first of all, you want to give all your data. So you want to fill in this entire table here, right? And make sure you include it in your lab report with your particular data, your particular values in here. And question 5 is going to ask you to compute the average height, the average diameter. So basically, you have to add up your height values, divide by 5, and make sure, this is important, make sure you round to the resolution of the instrument. So round to 2 places. Same thing for diameter. And then it's also going to ask you to compute the prad for height and the prad for diameter. Okay, and to compute prad, remember we went over that in a previous handout and in a previous video as well. So if you don't remember how to do that, make sure you look that up again or watch the video again. So you're going to calculate prad for height, prad for diameter, right, as a percentage. Okay, question 6 is going to ask you to compute the volume of the cylinder and the prad for volume. So to do that, let me jump over to the tablet to help you with this, to explain how this works. Okay, so again, we have a right circular cylinder, right? The aluminum cylinders are right circular cylinders where they have a radius and a height. And we know that to compute the volume of a right circular cylinder, and I'm drawing the base here, which is also a circle. The volume is simply going to be the area of the base, right, which is a circle. So it's going to be pi r squared times the height, right? That will be the volume of the cylinder. However, we're not measuring the radius, right? We're measuring the diameter, but there's a simple relationship, right, between the radius and the diameter. Remember, the diameter, I'll call it d, is twice the radius, so 2 times the radius. Or if I solve that for r, I can write this as the radius is half the diameter, right? Or diameter divided by 2. So when I ask you to calculate the volume, we can substitute this radius in for the formula for R here in the formula, and we can rewrite this in terms of the diameter. So if I substitute that in, I'm going to have pi. This is going to be d over 2, right, squared times h. And then if I expand it out, this will be pi d squared h over 4. So the first thing again that you have to do is compute the volume of the cylinder. So you're simply going to plug in your average diameter here and your average height, right, that you got from your table, and then calculate the volume. Okay, what about the second part of that question, of question 6? Now we want you to calculate prad for volume. We know the prad for diameter because you calculated it in the table. We know the prad for height, right? So the question is, how do we calculate the prad for volume? So if you remember, right, from the video where we talk about calculating prad when you have a formula that involves multiplying or dividing variables, then if I want to calculate the prad for this dependent variable here, the volume, and in this case, it involves multiplying diameter times height. Since it's diameter squared, you can think of this as diameter times height. And the other thing is, the pi and 4 are exact numbers. They don't have any error. It's just the variables that potentially have error, the diameter and the height. So you can ignore the exact numbers, the pi and the 4. And remember the rule now, if I want prad for the dependent variable volume, well, if I have a bunch of variables multiplied together, I have to add their respective prads. And since it's diameter times diameter, or diameter squared, I have to add the prad for diameter twice. So basically, the prad for volume is going to be the prad for diameter plus the prad for diameter plus the prad for height. Let me move this up a little bit. Plus the prad for height. And that will give you the prad for volume. Okay. So again, to calculate the prad for volume here, it's going to be the prad for diameter. So you're going to take this value, add another one, because you have to add it twice, plus the prad for height, right? So this plus another one plus the prad for height, that would be the prad for volume. Okay, the other thing that we need to measure to calculate density is the mass, right? So we have the volume now in centimeters cubed. Now we need to calculate or figure out, find the mass of the aluminum cylinder. So to do that, we're simply going to weigh it or mass it on a scale, right? So there's an electronic scale, electronic balance in the lab. It has a resolution. You got to be careful here. It's only one decimal place. It's zero point 0.1 grams. So you're going to mass the aluminum cylinder 5 times. Now, probably since the scale is really accurate, you're probably going to get the same 5 values, right? All these will be to one decimal place. So obviously that'll be your average. If that's the case, if these were all exactly the same, that means all your absolute deviations will be zero point 0, right? Or 0 0.0, 0 0.0, 0 0.0, 0 0.0. But then when you average these, remember you can't just use zero point 0 here. You have to use at least the resolution of the instrument for your average absolute deviation, right? If you don't remember that, refer back to the video on Prad. So remember, Prad can never be 0%. So you have to use at least the resolution of the instrument here for the average absolute deviation, which in this case is 0.1. So now to calculate Prad for mass, it's going to be 0.1 divided by your average mass times 100, right? And then that'll be your Prad for mass. Okay. But by the way, so make sure you include the table with all your data here for the mass. This is part of question 11 from the lab manual. And then the second part of question 11 is what we're really here to compute is the density. So here's the last table here. So you're going to compute the density of the cylinder. That's simply going to be the mass divided by the volume. The prad for density, right? And since it's mass divided by volume, you have to add the respective prads, and then the percent experimental error. To review this quickly, let me jump over to the tablet again. Okay, so again, remember density, and usually we represent density by this Greek letter rho here. So that stands for density, is equal to the mass divided by the volume of that aluminum cylinder. So you're simply going to take your average mass divided by the volume that you computed, and that will be your density. Okay, for the second part of that table, you want to find the prad for density. So prad for rho, right, for density. Well, remember, it's the same rule as previously. If I want to find the prad for this dependent variable here, in this case density, if the formula involves either multiplying or dividing, this is true for either multiplying variables together or dividing variables, then the rule is you always just add the respective prads. So in this case, to find the prad for density, you're simply going to take your prad for mass, which you calculated earlier in the previous table, plus your prad for volume, which you calculated earlier. And that will be the prad for density. And then finally, the last thing you have to compute is the percent experimental error. So percent experimental error for density. And that's when you want to compare your experimental value. I'll call this like EXP for experimental value. So that's your rho experimental to the accepted gold standard predicted value, which in today's lab, we're going to assume is 2.70. So the if you look this up on Google or something, the accepted value for the density of aluminum is 2.70 grams per centimeters cubed. Okay. Yeah, by the way, I should mention the units here, right? Since density is mass divided by volume, remember our mass we measured in grams in this lab, and the volume was centimeters cubed. So it's grams per centimeters cubed. So to compute the error, you're going to take your experimental value for your density minus the accepted value, which I'll just write as 2.70. But remember, we don't really care how we subtract that because we're making it positive. So it really doesn't matter what order you subtract in. You're going to take the absolute value. But the key thing is, what do I divide by? What's in the denominator here? It's always going to be the accepted value, right? The accepted theoretical predicted value, which in this case is 2.70. And then to make that ratio a percent, I just multiply by 100, right? So this will end up being a percent. So that'll be your percent experimental error for the density. And that could be zero, right? If you calculate your density and you got exactly 2.70, then this could be 0%. And that's great. That's fine. For error, it's okay to have 0%. It's only PRAD that we can never get 0%. Okay, and then once you have that, then the first part of the lab is done, right? The density of aluminum cylinder, that part of the lab is complete. For the second part of the lab, what we're going to look at is we're going to look at the relationship between the period and length of a simple pendulum. Okay, in lab, I'm probably going to have you collect data using the physical wooden pendulum, the actual physical pendulum. But you could do this using a simulation of a pendulum, and I'll use a simulation in this video just to show you how this actually works. So let me go to the simulation to show you what a simple pendulum is. And then I'll show you how to compute the information that we need in this table. Okay, so here is the simulation of the simple pendulum. So you can think of a simple pendulum as a mass, like some people call this a bob, that's suspended from a lightweight rod, or it could just be a string. And basically what we do is we displace the mass by a small angle, say maybe 10 degrees, release it, and it's going to oscillate back and forth. And the time for one oscillation is considered to be the period of the pendulum. So in other words, the time it takes to go from here, let me stop this, pause this. So the time it takes to go from here at -10 back to -10, that time is going to be the period. So the time for one oscillation. Okay, in terms of the variables here, if you look up in the simulation, we can adjust the length. So we're going to want to do this. We want to calculate the period for several different lengths. So these are meters. Um, if you go all the way down to the smallest, that's 0.1 meters, right? Which is the same as 10 centimeters, right? So if you multiply by 10, you can get it in centimeters. Sorry, multiply by 100 to get centimeters, or zero point 0.2 would be 20 centimeters and so on. The mass you can just leave. Actually, the mass turns out it doesn't matter, but we'll just leave it as 1 kilogram and we'll leave it 1 g, so 1 Earth gravitation with no friction. All right, so what we need to do is we need to find the time for 5 oscillations. So to do that, I have a stopwatch here, right? If it's not there, you can just click on stopwatch. By the way, there was a ruler that came up initially. We don't really need the ruler, so I'll just get rid of the ruler. And then what I would do is displace this to a small angle. It doesn't have to be exact, but usually like -10, even -20 would be okay. I'll just do -10 degrees. I'm going to press pause, which I already did, so it stays there. I'm going to press play on the timer. It won't start immediately until I press play down here. So I'm just going to press play so it's ready to start. And then as soon as I press play here, I'm going to keep track, right, of how many oscillations it's undergone. And then I'm going to stop this once it completes 5 oscillations. Okay, and that'll be the time for 5 oscillations. So I'll start this and count 1, 2, 3, 4, 5. And I stopped it at 5 oscillations. So it took 6.52 seconds, right, to undergo 5 oscillations. Then to reset this, hit pause again, go back to -10, hit the reset on the timer here, hit play, adjust the length because now we need to do a different length. Let's say it's 50 centimeters now. And then I hit play again and then count the time. 1, 2, 3, 4, 5. Stop it after 5 oscillations. So that'd be the time for 5 oscillations at 50 centimeters. Okay, so you're going to do that for each length from 10 centimeters all the way to 50 centimeters. And really, that's all the data that we need for this. Okay, so now we have our times. Oh, actually, I just noticed in this particular table, I think I changed this in the lab manual. I actually have you do it for 10 oscillations. So it doesn't matter if it's 5 or 10. In this case, okay, let's assume we did 10 oscillations for each of those lengths. So we measured the time for 10 oscillations. So to calculate the period, remember by definition, the period is the time for one oscillation. So I'm simply going to take this value, and by the way, this should be the 2 decimal places, and divide it by 10, right? And that would be the time for one oscillation. Or if you had found the time for 5 oscillations, you would take this value and divide by 5 to get the period. Okay, so it depends on how many oscillations you collected the time for. You just divide by the number of oscillations, and that'll give you the period. And then once we have the period, the other thing that we're going to need to compute is the period squared, where we literally just multiply the period by itself, right? We square that value. So you're just going to square these values on your calculator, and that'll go in the last column here. Okay, now again, all of these should be the 2 decimal places. So the only data that you're actually recording, that you're collecting, either from a physical pendulum or from a wooden pendulum, is the time for 10 oscillations, right? Or 5 oscillations. It really doesn't matter. Okay, in terms of the questions from the lab manual for this part, the first question is going to ask you to calculate the period versus the length of the pendulum. So you're going to plot this column, the period will be on the y-axis, and the length will be on the x. Remember, period versus length means y versus x. And then 17 is going to ask you to plot period squared. So you're going to plot this last column versus the length. And then question 18, and I want to go over question 18 first, actually, says using the results from question 17 when you plot period squared versus length, we want you to come up with an equation that gives the period as a function of the length. So we want an equation that gives you the period in terms of the length, okay? So let me help you with that first, and then these questions will make more sense. Let me explain like how this works. Actually, to do that, I'm going to bring up one graph from that first handout, from the measurement handout that we looked at. Okay, so this is from like the fourth page of that measurement handout, where there's a graph there, which is the period squared, right, of that simple pendulum versus the length of the simple pendulum. So period squared is plotted on the y-axis, length is plotted on the x-axis. And notice that when you do this, and you guys will discover this when you actually do this plot on Pascal Capstone, it turns out that period squared versus length is going to be linear, right? So you're going to have this nice linear fit to the data. Okay, so we're going to use this to actually help us write an equation that gives the period as a function of the length. So first of all, what's the um, what's the easiest way to write the equation of a line? Well, if you remember back from algebra, probably the simplest way is using the slope-intercept form, right? Y equals mx plus b. So let me jump over to the tablet a little bit more to explain this more carefully. Okay, again, so probably the most general way to write the equation of a line is in the slope intercept form, y equals mx plus b, where remember the m here represents the slope of the line, and the b is the y-intercept, right? It's where the line passes through the y-axis. So in this particular case, because that line, it turns out it pretty much passes through the origin, we're going to assume that our b is 0. So we're going to assume that b is 0 here. And the y variable, well, what was plotted on the y-axis? It was actually period squared, right? So remember, period we represent by t, the capital T. So the y here is really going to be period squared. And that's going to equal the slope of that line times x. But what was the x variable? Like, what did we plot on the x-axis? That was the length of the simple pendulum. So let's give that a name. Let's maybe call it L. So I have t squared is equal to m times L. But remember, this question, this last question, question 18, is going to ask you for an equation that gives the period as a function of the length. Right now we have period squared. So mathematically, how could I get period if I have period squared? Well, I could take the square root, right, of both sides. So if I do that, and technically you have to allow for the fact that it could be positive or negative, but we're going to take the positive root. So I'm just going to use the positive root here. So I'm going to have t, right? Square root of t squared is t, equals, and I'll write this as square root of m times square root of L. Okay, remember the rule, if I have the square root, right, radical a times b, I can split this up into square root of a times square root of b. So that's what I did there. Okay, so we're almost there, right? The only thing that we can, remaining thing that we can fill in is we can actually put in our slope, right? We will have the slope of the line from the period squared versus length graph. When you guys draw that graph using Pascal Capstone, right, and you do a line of best fit, it'll give you that slope value. So you can plug in your particular m here, your particular slope value. Now, typically it's around 0.04, like 0.04. I'm going to assume it is exactly that in this case. So I'm going to go further. You will have to use your particular value, but I'm going to assume for me it's 0.04. And then if I take the square root of 0.04, that turns out to be zero point 0.2. So I can rewrite this as t equals 0.2 times square root of L. And that's it. That's exactly what we want. This gives an equation, right, that gives the period, so the period t here, as a function of the length. It turns out in this case that it's like a square root function. Okay. If you were to plot this, right, what would this look like? Because actually, this is the other graph that you need to plot. So if you were to plot this, what would this look like? Well, to make it easier, let's do an easier problem here. Let's plot. So I'll plot period versus length. Right, this is in centimeters. Period is in seconds. And let's assume, let me make some more room here. Let's assume that my equation, just to make it easier, is t equals square root of L. Okay, so instead of 0.2, I'll just have a 1, just to make this a little easier. So if I have a little table here, if L is 0, or if I plug in 0, right? Square root of 0 is 0, so t would be 0. If I plug in, say, 1 for L, then square root of 1 is 1, so t is 1. If I plug in, I'm trying to think of easy values here, let's say L is 4, then the square root of 4 is going to be 2, so t would be 2. So if you plot these values, right, let's say this is, so 0, 0 is right here, 1, 1 is right here, 4, 2 is, say, here. Then this curve will look something like this. It'll look like a sideways parabola, right? It's a square root function. So when you do this graph, you should have this nice square root function. Okay, and then when you plot period squared versus length, it should be a linear function, right? In fact, that's how we're able to derive this equation here by using the period squared versus length graph, because that one should be linear. All right, one last thing. Let me jump on Pascal Capstone to show you guys how to draw the period squared versus length graph, because this is a little bit different where we have to do this square root function fit, and that's not one of the options. So let me jump over to show you guys how to do that. Okay, so remember in Pascal Capstone, what we want to do is once we start it up and you get this main page here, go to Classic Templates. And then we almost always use this upper left-hand icon here with the table and the graph. So I'll click on that. Then for the X variable, I want the length, right, of the pendulum. So I'm going to do the select measurement, create new, user enter data. I'll call this length. And then I'll hit tab and do cm for centimeters or units. Then for the next column, select measurement, create new, user enter data. Let's do period. And then for units, I'll do seconds, right? S for seconds. Okay, for the length, we had 0. Actually, I'm going to make up some nice easy values for me that will work out better. Let's say I have 0. Um, let's say 1, 4, 9, 16, 25. And then for periods, let's say I get 0. I'll vary these a little bit. Let's say I get 1.1, I don't know, 1.9, 3.2, 4.0, and then 5.1. Let's say those are my values. Okay, so when I plot this, remember on the x-axis, I want to choose what I want to plot here. Well, that's going to be the length. On the y, I need to choose period. Okay. For the title here, remember we can always use the y variable versus the x, so I can just call this period versus length. And then it does the one thing that we don't want it to do, right? It connects everything by default from with line segments. So remember how to get rid of those. If you hover over one of the data points and right click. By the way, if you have a Mac, sometimes you have to hold the control key down while you right click to get more fine control over it. Um, and then you want to uncheck show connecting lines. Okay, so hover over data point, right click, uncheck show connecting lines. Okay, and then normally to do a fit now, we choose in the menu here. Remember to make sure you keep this on, right? Because if you click to the left of the arrow, that turns it on and off. So make sure it's on. And then the arrow allows you to select what fit you want. And in most labs, we're probably going to use like linear, maybe quadratic. But in this case, we need a square root function, and it's not easy to get that here because it's not one of the options. So what we're going to do is we're going to do what's called a user defined function. We'll define it ourselves. So I'm going to click on that. By default, it's going to use a line, like a linear function. So this is like ax plus b instead of mx plus b. They just call it ax plus b. So we want to change this to be like a square root function. So to do that, if I click on this information, you'll notice on the left-hand side of your capstone, it'll bring up this curve fit editor. So we're going to click on that. And then here where it says y equals, this is the equation that we want to fit it to. So there could be some constant out front a, so I'll leave that a times, and then I'm going to do sqrt parentheses x close parentheses. So that defines like a general square root function. And then if I hit apply here, it should actually do the nice fit. If for some reason it doesn't work, it doesn't, sometimes you'll get like a little error here, like it doesn't do the fit well. What you can do is you can put an initial guess in here and you can use like 0.2 because it's probably the A is probably going to be around 0.2-ish and that may work better. But in this case, it should actually figure it out for you. Okay. Actually, no, I guess in this example it would be one, right? I guess one would work out best. So it should just work well with one here. In the actual lab, if you're doing this for your actual lab information, then you might have to put 0.2 as an initial guess. But even if with one, it should work in most cases. Okay, I don't need this anymore, so I'm just going to click on the curve editor again to get rid of that. And now I have all the information I need, right? I have my labels with units. I have a nice title, period versus length, and I have my graph here with a nice square root function fit, right? So now if you want to include this in your lab report, you can hover over the border here, right click, and just go to copy display, and then you can paste it into your lab report, right? If you're using Google Docs or a Word document, however you guys are sharing the information for your group lab reports. Okay, so that actually is question 16, right? To do this graph. Question 17 is similar, except you're going to now plot periods squared. So you either need to change this or do another column, period squared versus length, and that one should be linear. All right, let me go right back to the handout to finish this up. Okay, so again, question 16 was to plot period versus length. This is the one that should be a square root function, the one we just went over on Pascal Capstone. Also, don't forget to answer the question. If you look at the actual lab report, it'll also ask you to describe the shape of the graph, right? So you want to do the plot and then describe the shape. You could just say it's curvilinear or it's a square root function, something like that. 17 was plot period squared. So this information will be on the y-axis and length will be on the x. This one should be linear, right? It'll also ask you for the shape. So again, it should be linear. Make sure you answer that question though about the shape. And then question 18 is what we just discussed, right, on the tablet. You want to come up with an equation that gives the period as a function of the length. So now, and we know it's going to be t equals square root of m times square root of l, but now you know your slope, you know your m, your slope. You have that from question 17, from that graph, from the period squared versus length graph. So you can plug in your particular value for m here, and then you can get your exact function. It'll be t equals whatever the square root of your value is of your slope times square root of l. right? Typically, it'll be around t equals somewhere around zero point 0.2 times square root of L. Okay, and then that's it for the first lab. Thanks.